Welcome to AI Peer Review, where we analyze the latest technical reports, extracting the signal you need to stay sharp. Our mission today is laser-focused. We're doing a deep dive into a really interesting new world model called Pan.
Right.
And this one feels different. It's trying to move beyond, the spectacle of just beautiful video generation.
Mm-hmm.
Okay, let's unpack this. If you think about a model like Sora, the visual fidelity is it's incredible. They can create these stunning videos.
Absolutely.
But they work in this sort of prompt-to-video way. They don't have that real-time causal control or, and this is the key part, the long horizon consistency that an agent really needs to plan or run, thought experiments.
And that fragmentation is the exact problem they're targeting here. It's the central challenge.
So what's the landscape look like right now?
Well, you're forced into a choice. You either get these models with amazing visual realism, but they lack any kind of sustained, reliable dynamics. You can't really control them. Or you get world models that are stuck in these really narrow domains. Think a specific video game or a very controlled robotics lab. They just don't have that open domain generality.
And Pan is trying to be the bridge.
Exactly. It's presented as this general, interactable, and long-horizon world model.
Mm-hmm.
It predicts the future based on history and natural language actions.
So it's unifying internal reasoning, what they call imagination, with actual grounded world dynamics or reality.
Right. It's trying to build a brain that can accurately simulate the world, not just, paint a pretty picture of it.
So if that's the goal, let's talk architecture. They designed something called Generative Latent Prediction, or GLP. Why is it so hard to manage those two things at once? The internal simulation and the external observable world.
Because they're sort of at odds with each other. I mean, if you make your latent space too flexible to imagine complex things, it can just drift away from anything physically possible.
And if you tie it too closely to the pixels,
You lose the power to generalize. So GLP tries to balance this. There are three main components, and you can see this laid out in Figure 1 of the report.
okay.
First, you've got the vision encoder. Let's call it $. This is your foundation. It takes in a raw observation, like a video frame, and compresses it into a compact, latent state.
A summary of the world.
A summary, exactly. Then you have the real engine, the predictive module, or the backbone, which they call $4. This is the part that models the world's dynamics. It predicts the next state based on the current state and an action.
That's where the causality lives.
That's right. And finally, the decoder, $2. Its job is simple, but absolutely vital. It reconstructs what you would actually see from that predicted latent state. It anchors the whole simulation back to reality.
Okay, this brings us to what feels like the core methodological shift here. Something they call generative supervision. Why is this better than what came before? Let's contrast it with a model like JOPA.
Right, GPU was really a pioneering idea. It tried to do everything in that latent abstract space. It would basically say the encoding for frame A should be mathematically close to the encoding for the real frame B.
It's just matching feature.
It's matching features. But the problem, and this is a really deep technical point in the source, is that GPU can suffer from collapse and this thing they call the indefinability problem.
What does that mean in practice?
Well, imagine the model is looking at a teacup on a table. The math in that latent space might say the feature vector for that teacup is actually close to the feature vector for, say, a spaceship.
Because they're both complex objects.
Exactly. Semantically, maybe they're both complex. But physically, that transition from a teacup to a spaceship is impossible. The latent space prediction is unconstrained by real-world physics.
It's not grounded.
Ungrounded, that's the perfect word. Pan's generative supervision fixes this. It uses a flow matching loss to ensure that every single transition in the latent space must correspond to a realistic, high-fidelity change you could actually see. It ties the imagination to reality.
Now, here's where the implementation gets really clever. They don't just build this from scratch. They use a hybrid of a vision language model and a diffusion model.
Mm-hmm.
The vision part comes from Qwen 2.5 VL. But the really big choice, I think, is that the backbone, that core predictive part, $5, is the language model from that same VLM.
And that's the secret sauce. That's what gives it generality. By using an LLM, Pan gets to tap into this massive reserve of common sense physics, object permanence, and just, world knowledge from all its text pre-training.
Things a purely visual model would never know.
Never. And that LLM is what maintains global temporal consistency over these really long time horizons. It conditions its prediction on the entire history of states and actions.
And the actions themselves are just natural language, right?
Just plain English. They're fed in like a multi-turn conversation, which fits the VLM structure perfectly and makes the whole simulation completely steerable.
Hold on a second, though. If you're running causation through a massive 7 billion parameter language model, isn't that incredibly slow? I mean, what's the trade-off for an agent that needs to plan in real time?
That's a great point, and it's a very real engineering trade-off they're making.
Hmm.
The LLM backbone is computationally expensive, yes,
So why do it?
because they're dedicating it to the hardest problem.
Hmm.
The high-level, structured causal dynamics. It's figuring out what should happen next based on deep knowledge.
And it leaves the pixel pushing to something else.
Exactly. The visual fidelity, the fine details, that's handled by the decoder, which is a video diffusion model. It refines the LLM's prediction into a smooth, detailed video clip. It ensures local consistency, freeing up the LLM to focus on the big picture. It's a trade of speed for reliability.
Okay, but even with this hybrid system, any kind of sequential generation has an Achilles heel, temporal drift,
Hmm.
errors add up, and the simulation just falls apart. So they need something specific to combat that.
They did. And that mechanism is called the Causal Shift Window Denoising Process Model. Let's call it Causal SWIN DPM.
A bit of a mouthful.
It is, but what it does is really elegant. It's designed to stop those abrupt, jarring jumps between video chunks and prevent the slow buildup of
How
artifacts.
does it work?
It uses a sliding window that's looking at two chunks of video at once. But, and this is the key, there are different noise levels. You can see it in Figure 3.
Why add noise? That seems counterintuitive if you want consistency.
It's a trick to manage uncertainty. Instead of looking at the previous chunk in perfect, pixel-perfect detail, which is full of random, incidental noise that's impossible to predict,
Ah,
it looks at a fuzzy, partially noised version of the past. This forces the model to ignore all that pixel-level randomness and focus only on the high-level semantic consistency,
things like where objects are and what they are. The important stuff.
the stuff that matters for keeping the simulation coherent over time. It's penalized for breaking the story, not for getting a few pixels wrong.
And that causal attention mask is for making it interactive, for real-time use.
Absolutely. The mask ensures the model only ever looks at the past. It can't cheat and peek at the next action you're about to give it, which keeps the causality pure while making sure the transition is super smooth.
The proof is in the pudding, of course, the evaluation. They went way beyond just asking if the videos look nice, which I found refreshing.
Yeah, they tested it on 3 dimensions that really matter for a world model. First was action simulation fidelity. Basically, does it do what you tell it to do?
And
It scored 58.6% accuracy, which beat all the open source models and even most of the commercial ones. It shows it has a really strong grasp of action-driven change.
what about holding up over time?
That was the second test, long horizon forecast. On transition smoothness, it scored 53.6%, which means very few jarring cuts. But the big one, simulation consistency, where they measure how much it degrades over time, it got 64.1%. That massively surpasses its competitors. Simulation doesn't just start strong, it stays strong.
And now we get to the real point of all this, simulative reasoning and planning. Can an agent actually use this to think?
Right. On a simple stepwise simulation test, like for robotics, it scored the highest among open source models. But the truly compelling result, and you can see the process in Figure 4, is when they integrated PAN with a VLM agent, OpenAI O3.
So they let the agent use PAN for its thought experiments.
They did. And when the agent could use PAN as an internal simulator to test out plans before acting, they saw a 26.7% increase in task success for open-ended planning,
Wow.
and a 23.4% increase for structured planning. And those numbers are compared to the same VLM agent without the simulator.
Those are not marginal gains. That's the difference between an agent that usually fails and one that reliably gets things done. It proves that just looking pretty isn't enough.
Precisely. It proves that PAN's reliable, grounded, causal simulation is the essential ingredient for complex, multi-step decision-making. It's giving the agent a truly reliable sandbox to play in.
So to wrap this up, PAN feels like a massive step forward. It unifies that grounded reasoning and physical simulation with long horizon interactivity, all thanks to that GLP architecture and the causal SWIN DPM stabilizer.
It really does. It functions as a totally self-contained simulator. Each prediction it makes becomes the basis for the next one, creating this long, coherent stream of imagination that is always, always anchored back to what's physically possible.
And that leaves us with a final thought for you to chew on. If a model like this can reliably simulate complex counterfactuals, these rare events, these long causally sound scenarios, all on demand, what is the practical upper limit of using that synthetic data to train the next generation of AI agents? That capability could fundamentally change how we scale AI from here on out.